Hello, I would like to talk to you today about something called synthetic division. It does involve division, much in the way that you probably think about division from way back in like fourth grade when you first learned how to divide numbers. Except we are going to work on dividing polynomials. So let me do a quick recap of how to do long division with polynomials. And then I'll get into synthetic division and like what that means and how it matches up. Let's say that you have the polynomial x cubed plus 7x squared plus 13x plus 6. And you want to divide that by the polynomial x plus 2. So we have polynomial division we're doing. So you can take the first polynomial, and that is your dividend, so that goes on the inside. X cubed plus 7x squared plus 13x plus 6. And you can divide that by the divisor, x plus 2. And then, your quotient's going to go up above your dividend, and then your remainder will get written up there with the quotient as well. Okay, so long division. We take the first term in that divisor, the x, right here, and we think about that multiplied by what would give us this first term in the dividend. So we say, well, x times x squared would give us x cubed. So we go ahead and put x squared right here. We keep everything lined up as far as degrees. So like all your x cubed terms will stay lined up, all your x squared terms will stay lined up, all your x terms, all your constants on the end there. And then below that, just like a normal division problem, we're going to multiply the x squared that we just put up there in the quotient times the x plus 2. So just think about like if you took x squared times x plus 2, how that would work out. You'd distribute, so you'd get x cubed plus 2x squared. So that's going to go down below. Keeping everything lined up with the cubes, the squares. Then just like a regular division problem, we're going to subtract, see what we get, and then bring down the next term. But keep in mind you're subtracting that entire expression there, the x cubed plus 2x squared. So you have x cubed minus x cubed is 0, x cubed there. And then you have 7x squared minus the 2x squared. So that's going to give you plus 5x squared. We no longer have to worry about the x cubes because we've got a 0x cubed. But we are going to have to worry about the 5x squared after we bring down that next term of plus 13x. Okay, so now that x again in the divisor, and now we're going to think about this 5x squared here down below. Well, if we multiply x times plus 5x, that would give us 5x squared. So we're going to do 5x times x plus 2. 5x times x is 5x squared. 5x times plus 2 is plus 10x. We're going to subtract. We get 3x. Bring down. I'm not even going to write. I'm not going to bother writing this. I will for this example, but in the future, I'm not going to write like the 0 terms like that. I will for now. 0x squared. We got plus 3x, and then we'll bring down the plus 6. So now we'll think about this 3x leading right here. Well, x times plus 3 would give us 3x. So 3 times x plus 2 is 3x plus 6. Sorry, I'm running out of room here on this little slide, but we know we get 0. So we know we get a remainder of 0. All right, so the solution, the quotient is x squared plus 5x plus 3 after we carry out that division. So yeah, we had our dividend here. We had our divisor here. and we had our quotient here with the remainder. Okay. I apologize for squishing this in, but I promise synthetic division doesn't require quite as much room. So we just did long division. That required a lot of space. Synthetic division requires way less space. How do we do synthetic division? Well, we take that dividend and we just write down the coefficients, including the constant down on the end. So like for x cubed, the coefficient is a 1. For 7x squared, the coefficient is a 7. For 13x, the coefficient's a 13. For 6, it's a 6. Then it's going to be kind of an upside down sort of nature here. So then we're going to think, all right, our divisor is x plus 2. So we're going to ignore the x and just take the plus 2. And we're going to use the opposite of that. We're going to use negative 2. And I'll explain why in a minute. So for now, I'm just telling you like the mechanics of how this works. And in a minute, I'll explain what exactly is happening. Okay, so we bring down the first number, the 1. Then we're going to multiply that negative 2 and the 1, and we're going to get negative 2. So we'll put that over there under the 7. And then we're going to add the results and get 5. Take the negative 2 times the 5, we get negative 10. Put that under the 13. Add the results, we get 3. Take the negative 2 times the 3, we get negative 6. Put that over here under the 6. Add the results, we get 0. And then we're basically done. We have to write up our answer still, but that's basically it for the division. Way less space, way less time. Now with synthetic division, we're focusing on using a lot of the coefficients on that dividend, and it translates to the quotient also gives us the coefficients, those numbers that go in front of the variables. So now to write out the answer, we just keep in mind that those are our coefficients and then fill in the variables. With synthetic division, your first term is always going to be a degree 1 less than the dividend's first term. So like in our dividend, we had x cubed plus 7x squared plus 13x plus 6. Our quotient isn't going to start with an x cubed, but rather it's going to start with an x squared. So we have a 1x squared, and then it just counts down with the degrees from there. So we have a plus 5x, because that would be like x to the first, then plus 3, and then the remainder on the end here is 0. So that's our solution. That's our quotient, x squared plus 5x plus 3. We got the same thing that we had gotten earlier in the long division. It's just we cut out a lot of the stuff being written. Well, let's look at this for a second. All right, in the long division, essentially we were looking at our coefficients when we were trying to decide what to multiply by. Like when we figured out, well, x times what gives us x cubed? Well, we knew that we had to have a 1 and then an x squared. And then later on, like x times what gives us 5x squared? We knew we needed a 5 and then an x. And then later on, x times what gives us 3x? We knew we needed a 3. So in all of those, we were looking at like what were the coefficients needed. And then the variables just kind of fell into place, counting down. We started out with a degree that was 1 less. So instead of x cubed, we start out with x squared. So we know that's going to happen each time in these synthetic division problems. And then notice that, as we were working it out, as we went down the way, we were doing a lot of subtracting. You're like, well, yeah, that's how it works when you're doing division problems. You subtract and see what's left. Well, since we knew we were subtracting, for synthetic division, that meant we could just use the opposite of what was in that divisor there and then add when we were dealing with finding our results, finding our coefficients. So we didn't have to subtract because we were already using that opposite number there. We didn't need to use the x because we knew how that was going to play out automatically. Since synthetic division, you're going to be starting, your divisor is going to be a 1x, then plus or minus some constant number. So rather than write all these x's over and over again, we just ignore, we just for now just don't write them and then fill them back in later in the answer. As we were thinking about what to multiply, you notice that like the 5 here worked out right here. Notice that the 3 here worked out right here. Oh, don't want to leave the 1 out. Like technically we were thinking about the 1. That's how that worked out. So we had the 1, and we had the 5, we had the 3, and then that lovely remainder 0. I don't have any other colors, darn it. I'll just use red again. Yeah, that 0 there worked out in the synthetic division as well. So it's really nice. So that in a nutshell is how you do the division. Okay. So for synthetic division, the divisor must be a first degree binomial of the form x minus k. If it's not of that form, if it's not, then long division is used. And knowing it has to be of that form in order for synthetic division to work, that's exactly why we can set it up and for temporarily ignore all those variables. And just work with what's happening with those numbers. And the fact that x has a 1 in front of it makes a huge difference. All right, let's do a couple more examples. Let's say you have something like negative x cubed plus 8x squared plus 0x plus 63, and you're dividing it by x minus 4. All right, in the book or in your homework or whatever, you probably won't see that 0x written. They'll probably skip right over it and just say negative x cubed plus 8x squared plus 63. But it's important to make sure that all of your terms count down and don't skip any numbers in those degrees. So like degree of 3, degree of 2, it skipped degree 1, so we got to put a 0x in there to have that degree 1 represented. And then the 63 is a degree 0. If we were doing this long division, that first polynomial is the dividend. It goes on the inside. That second polynomial is the divisor. It goes on the outside. We know in our heads that we can do synthetic division instead because the divisor is x minus 4, where the k is the 4. So it's in that format that we need. But let just for demonstration, let me go ahead and show you the long division, and then I'll skip over and do synthetic right next to it. All right, so x minus 4. The x times what would give me negative x cubed? Well, I know that that would be negative x squared. So keeping all my cubes and squares and x's and constants lined up over here. So I get what? Negative x cubed plus 4x squared. And since we're doing long division, we'll subtract. I'm not going to bother to write 0x cubed. You know that that's what comes out right there. I don't need it right now. So I'll write 4x squared. Then I'll bring down the plus 0x. I need that 0x in there like right now to hold a place and to have something in case, you know, I get a next term pops up, which it's going to right now. Because I'm going to put a plus 4x up here, because that's precisely what I need to get that 4x squared. And then minus 4 times 4 is minus 16x. Perfect. I have that 0 to subtract 16, negative 16 from. So I end up with 16x. Bring down the plus 63. I get plus 16. So 16x minus 64. Subtract. And this one ends up giving me a remainder. So I get negative x squared plus 4x plus 16 with a remainder of 127. All right, off to the side, let's see the synthetic division version of this. The dividend has coefficients of negative 1, 8, 0, and 63. Even with synthetic division, I cannot forget to put that 0 there. It's necessary. I need everything to count down properly. You know, I have that luxury of leaving out the x's, but we don't want to mess things up by leaving out a degree that's going to be necessary, possibly be necessary. All right, and then on the outside, remember, instead of, like, since it's x minus 4, we're going to use the opposite of plus 4, so that way we can go through and do some addition instead of worrying about subtracting. Nobody really enjoys subtracting, so if we know we're adding each time, it makes it much easier. All right, bring down negative 1. That automatically just comes down. Then do your 4 times negative 1, which gives you negative 4. Add 8, negative 4, you get 4. Do 4 times 4, you get 16. Add 0 and 16, you get 16. 4 times 16, 64. Add 63 and 64, you get 127. So now we have all of our coefficients laid out here. Now notice, you know, each time your answer is going to start with a degree less than what the divisor started with. So it's not going to start with x cubed, but rather x squared. So negative 1x squared plus 4x plus 16, remainder 127. Now, if you want to, instead of writing negative x squared plus 4x plus 16, remainder 127, you can write negative x squared plus 4x plus 16 plus, and then you can put the 127 over your divisor, x minus 4. And that is another way to write your answer. And that's probably the one you're going to see more often. Interesting, huh? Why can we do this? Well, we have something called the division algorithm. Division algorithm, you have f of x and g of x are polynomials. G of x has lesser degree than f of x. So in other words, its leading term has a smaller exponent than f of x does. So g of x has lesser degree than f of x. G of x has degree 1 or more. So there exists unique polynomials Qx and Rx such that f of x equals g of x times q of x plus r of x. Either r of x is 0 or the degree of r of x is less than the degree of g of x. Okay. So in our problem, we have our f of x being divided by our g of x. So the f of x is that dividend. G of x is the divisor. Q of x stands for quotient, so that's a nice, easy thing to remember. Then r of x is the remainder. So this is saying that if you take your divisor times your quotient and add your remainder, then you get the same thing as the dividend. Okay, let me show you a numeric example, which you probably learned this back in like 4th grade. 127 divided by 4. If we set up the long division problem, 127 is our dividend, 4 is our divisor. So 4 goes into 12 3 times, 0, bring down the 7. 4 goes into 7 1 time, remainder 3. So 31's the quotient. 3 is the remainder. Okay, according to the division algorithm, 127 equals 4 times 31 plus 3. The dividend equals divisor times quotient plus remainder. So let's work it out. 4 times 31 is 124, and 124 plus 3 is indeed 127. So that works out. Yay! Also, a remainder of 3 means you have, when you're dividing by 4, you're dividing things into 4 parts each. So like, let's say you have a bunch of pizzas. You have 127 slices of pizza, and each pizza was divided into 4 slices each. You know that you'd have 31 whole pizzas with 3 slices hanging out still. So those 3 slices would be 3/4 of a pizza. So you'd have 31 whole pizzas plus 3/4 of a pizza. And 31 3/4 times 4 also equals 127. If you have 31 3/4 pizzas times 4 slices per pizza, that means you have 127 slices. So that's what's going on with the division algorithm. And so those principles apply also when we're dealing with our polynomial functions and trying to do our division or polynomial expressions, and trying to deal with those division problems. Okay, let's see here. Let me do another one. Let's do 2x to the 4th plus x cubed minus 15x squared plus 3x. And let's divide that by x plus 3. Okay, notice that we're missing a term right there. We count down from 4 to 3 to 2 to 1, but we don't have a 0. So we're going to have to make sure we fill that in when we do our division. All right, let's jump straight into just doing synthetic division. So let's do, I was going to do long division also, but I'm not going to do that today. So we write down the 2, the 1, the negative 15, the 3, and then don't forget a 0 on the end there so that so you don't miss any numbers counting down from the top exponent down to 0, the constant. All right, we're going to do synthetic division. And since we have x plus 3 for the divisor, we're going to use negative 3 out here. All right, bring down the 2. Negative 3 times 2 is negative 6. Add, we get negative 5. Negative 3 times negative 5 is 15. Add, we get 0. Negative 3 times 0 is 0. Add, get 3. Negative 3 times 3 is negative 9. Add, get negative 9. Okay, the original dividend started with an x to the 4th, so our answer is going to start with an x cubed and count down. 2x cubed minus 5x squared plus 0x plus 3 with a remainder of negative 9. So I'm going to go ahead and write this as 2x cubed minus 5x squared plus 3 plus negative 9 over x plus 3. Now if you went ahead and multiplied all that out with x plus 3, you would get back 2x to the 4th plus x cubed minus 15x squared plus 3x. As soon as you take that entire quotient times your divisor, you'll get back your dividend. Okay, let's talk about something called the remainder theorem next. If f of x is divided by x minus k, which is what we were just doing, then the remainder, this is a really cool little theorem. It's an offshoot from our division algorithm earlier. Then the remainder is f of k. You're like, what? What does that mean? All right, let's say we have our f of x be 2x cubed minus 3x squared minus 5x plus 4. And we're going to divide by an x minus k of x minus 2. So I'm just going to do synthetic division, quick and easy. I can do that because I have an x minus 2 for my divisor. So I have 2, negative 3, negative 5, 4. I don't miss anything in the countdown on the degrees there for those terms. And then x minus 2, let's use the opposite, plus 2. Bring down that first number. 2 times 2 is 4. Add, we get 1. 2 times 1 is 2. Add, we get negative 3. 2 times negative 3 is negative 6. Add, we get negative 2. So in this problem, you end up with 2x squared plus 1x minus 3 and a remainder of negative 2 for your answer. So the remainder theorem has to do with the remainder, hence the name. What it's saying is you can do the division to find the remainder, but another way to do this is to take your f of x, which is the 2x cubed minus 3x squared minus 5x plus 4, and evaluate f at 2, the k. Plug 2 into your function and see what you get. You should get back the remainder from that division. So the 2 that we're using comes from that k. All right, so let's plug her in. 2 times 2 cubed minus 3 times 2 squared minus 5 times 2 plus 4. So we get 16 minus 12 minus 10 plus 4. So we get negative 2. And there it is. We get the same thing. Isn't that cool? So you can always just take your function and plug in that k, evaluate it at that value, and whatever you get as your outcome is the remainder from the division problem. Neat, huh? All right, that leads right into talking about something called zeros of polynomial functions. Zeros are where the graph crosses the x-axis. Also, you might know of them as being x-intercepts. So at these places, the y value is 0. Okay. Let's say that we have a problem like x squared plus 4x minus 5, and we're dividing by x plus 5. If the remainder is 0, then we know we have an x-intercept value. And we have a 0 of the function f of x. Okay, in this case, f of x being x squared plus 4x minus 5. Okay, let's do a quick synthetic division and see what we get for our remainder. So we'll put a 1, a 4, and a negative 5 from the f of x, because it was 1x squared plus 4x minus 5. And then we're going to divide by negative 5, because x plus 5 is the same thing as x minus negative 5. So the k is negative 5. Bring down the 1, multiply, add, multiply, add. Okay, so in our result we get x minus 1 with a remainder of 0. Yes, remainder is 0. So that tells us that negative 5 is a 0 of the function. If we wanted to, we could take f of x and evaluate it at f at negative 5, and we would get the same result. We'd get 0. Whatever that remainder is, that's going to be the same thing as evaluating the function at negative 5, at that k. So we have negative 5 squared plus 4 times negative 5 minus 5, plugging it straight into f of x. So we have 25 minus 20 minus 5. And voila, we get 0. So not only is negative 5 a 0 of the function, but negative 5 comma 0 is an x-intercept of the function. In fact, if you did a quick sketch of the graph, it would look roughly like this. It's a parabola. This is the parabola for f of x equals x squared plus 4x minus 5. And one of the x-intercepts is right here at negative 5, 0. It has another x-intercept at 1, 0. And it has a vertex down here at negative 2, negative 9. But you know that 1, 0, 1 is another 0 of the function. Like if you evaluated f at 1, you would also get 0. Or if you did the long division and used 1, you get a remainder of 0. That's where it crosses the x-axis. So zeros are another way of saying x-intercepts. Either in long division, you would end up with a 0 remainder, or when evaluating the function at that k, you'd end up equaling 0. So that k would be the x value where it crosses the x-axis, and then 0 is the y value. Pretty neat, huh? Okay, let's do one more. We've got the function f of x equals 2x cubed plus 9x squared minus 16x plus 12. And the question is k equals 1 a 0? So we're going to do a quick test and find out. We're going to do quick synthetic division and see if we get 0 as a remainder. So we have, in our original function f of x, we have coefficients 2, 9, negative 16, 12. Our terms, all the degrees count down, 3, 2, 1, 0, so we don't need to do any fillers. K is 1 that we're testing. If k equals 1 is a 0, then I expect my remainder to be a 0. Let's see what happens. Bring down that first number. 1 times 2 is 2. Add, get 11. 1 times 11 is 11. Add, get negative 5. 1 times negative 5 is negative 5. Add, get 7. Uh-oh. Answer starts with 1 degree less than the original f of x, so we have 2x squared plus 11x minus 5 with a remainder of 7. So no, not a 0. If we went ahead and evaluated f of x at x equals 1, we would get 7 as our answer that way as well. So we get 2 plus 9 minus 16 plus 12, which is 7. So yeah, notice those two are the same. They're supposed to be. So that is not a 0 of the function. In fact, if you went ahead and took that function, I put it in Desmos, in the graphing calculator in Desmos.com real quick, and I got the function, and it looks kind of like this. Desmos, when you click on the actual graph of the function, it'll take key points and go ahead and put dots there, and then you can hover over those key points and see what the coordinates are. So Desmos did several key points, including my x-intercept and my y-intercept. And including that relative max, relative min there on the and those two inflection points. So anyways, you can put it in Desmos and put your f of x in Desmos and see that. Now notice that the actual 0 is at negative 6, 0. So if we went ahead and did a long division with negative 6 instead, we would expect actually to get a 0 remainder, because that is truly a 0 of the function, or an x-intercept. And there it is. Yay, it worked. That's exactly what we would expect. Or if you evaluated the function at -6 and did it that way, you'd also get 0. And that's exactly what we expect. So, a couple different ways to think about zeros or x-intercepts. Make sure you learn this. This is going to keep coming back in this unit. We're definitely going to keep seeing this again and again. But you can either use your division, you can do long division or synthetic division. If it is a 0 of the function, you'll get a 0 remainder. Or you can always take that number and plug it into the function, evaluate the function at that value, and you should get 0 back if it's a 0. If you get anything else back, it's not a 0. Like on this function, earlier when we plugged in k equals 1, well, k equals 1, we got a remainder of 7. So we can find 1 comma 7 on the function. So it is a point on the function, k equals 1, y equals 7, but it's not a 0. It's not where it crosses the x-axis. But it is on the function. All right. Well, we'll come back and dive some more into polynomial functions. But for now, this was synthetic division. Hope you have as much fun as I did.